We talked about special angles last time. Those were angles in a right triangle, guaranteed by the geometry of a right triangle to be in size between 0 and 90 degrees. But it's certainly possible to have angles that are bigger than 90 degrees. This angle has an initial side in standard position being the positive x-axis and a terminal side all the way around in quadrant 1, 2, 3, quadrant 3. So this angle has measure bigger than 180 degrees. The problem is that that doesn't fit in a right triangle. So if you want to extend right triangle trigonometry to this case, it won't work unless you make some special convention. The convention that you use to do a general angle bigger than 90 degrees, so that it would bigger than it would fit in a right triangle, is to make the angle determine a right triangle that has an appropriate size degree. Here, instead of taking the whole angle from the positive x-axis all the way around, the trick is to drop a perpendicular from the point to the x-axis, and then that does determine a right triangle, and the angle that's inside that triangle, this little piece of the whole angle starting at the positive x-axis, will work to come up with assigning values to the trig functions. So for a general angle, we will draw a reference angle in to be the acute angle that you get in the triangle gotten by dropping a perpendicular to the x-axis. And the reference triangle is the triangle that you get that way. The right triangle, maybe not positioned in quadrant 1, maybe in quadrant 2, or like this one is in quadrant 3 or quadrant 4, but it still makes sense to think about ratios of sides of the reference triangle to come up with values of the trig functions. So let's look at what's happening going around to this other position and getting a reference triangle that maybe doesn't use the entire angle but uses a piece of it to come up with the ratio of sides. The ratio of sides stays the same. If you set it up to come up with values of the trig functions, sine, cosine, tangent, it looks like the old SOHCAHTOA ratios that we talked about before. What's different here is that we're going to allow the values of A and B to be positive or negative, since they could be coordinates of a point somewhere in the coordinate plane, maybe positive, maybe negative, and we'll keep track of where we are in a circle by looking at a radius of the circle, and that's going to play the role of the hypotenuse. So instead of h in these ratio definitions, we'll write it as r for the radius of a circle, but it's still a ratio definition that determines a value for the trig functions. All that can go wrong is if, in this general case, you build a ratio that has a 0 in the denominator. If that happens, then we'll leave the trig function undefined for that configuration of points. So here's an example to see how it's going to go. This time the angle determines a terminal side in quadrant 2. And this point, -2, -3, coordinates in quadrant 2, will be what's relevant for building a reference triangle. Let's drop the perpendicular and look at the triangle that's so formed. The triangle that's formed has an A value and a B value, a side adjacent to not the angle but the reference angle, the part in the triangle that you've built, a side adjacent and a side opposite that angle, and it's given by the coordinates of the point. So -2 is the x-coordinate of the point on the terminal side. -2 would be the value you would assign to A, and B would be the value that you would assign to the side opposite that reference angle. That would be a positive 3 in quadrant to get the point in quadrant 2. So A is minus 2 and B is 3, and now we'll just turn the crank the way we've been calculating trig function values. R is playing the role of h, the square root of a squared plus b squared by the Pythagorean theorem, minus 2 squared plus 3 squared. 4 plus 9 is 13, so the square root of 13 goes under there. Sine is opposite over hypotenuse, in this case 3 for the side opposite and root 13 for the hypotenuse. So 3 over root 13, and we have the option of setting this up with a rationalized denominator. So 3 root 13 over 13 for the value for the sine of theta. Cosine is adjacent over hypotenuse. The value for a that we got from that point was minus 2, so minus 2 over root 13. And again, rationalizing the denominator, minus 2 root 13 over 13 for the value of cosine. Let's do tangent. Tangent is opposite over adjacent. Opposite was the signed number 3. Adjacent A was the signed number minus 2. Look at your picture for that triangle. 3 over minus 2, so minus 3/2 for the value of tangent. Now the other trig functions you can get by applying the reciprocal identities. Cosecant's the reciprocal of sine. So instead of 3 over root 13, it's root 13 over 3 for cosecant. Secant's the reciprocal of cosine, so instead of 2 over root 13, it's root 13 over 2 with a minus in front. And the reciprocal of minus 3/2 is minus 2/3. So since tangent was minus 3/2, cotangent of theta is minus 2/3. So we get all the trig function values out. Another thing we can look at is a limiting case. What happens if we actually have the triangle collapse to being actually on one of the coordinate axes? If r is equal to 1 and a point is 1, 0, 1 unit out along the x-axis, the effect of that is to have a triangle where the reference angle would be 0 degrees to go straight out along the x-axis for the terminal side. Well, if the side adjacent is 1 and the side opposite is 0, the hypotenuse is also 1 unit straight out. The limiting case would give r equals 1. And so the ratio definition for the trig function, sine of 0, b over r, 0 over 1 makes sense as 0. Cosine is a over r, side adjacent is 1, hypotenuse is 1. So cosine of 0 is 1. Tangent is opposite over adjacent, 0 over 1 makes sense as a fraction. Tangent of 0 would be 0. How about the reciprocals? Cosecant is the reciprocal of sine. Instead of 0 over 1, it's 1 over 0. That would be undefined, and the value of cosecant of 0 would be left undefined. Secant, there's no problem. The reciprocal of a over r, r over a, would be 1 over 1 for that limiting case. 1 comes out for the secant of 0, that's fine. And cotangent, the reciprocal of tangent, has the ratio 0 over 1 flipped, and again, that's a problem. So for the value of the constant 0 for the angle, tangent of 0 and sine of 0 both are equal to 0, which means the reciprocal identities, reciprocal of sine is cosecant. Cosecant of 0 is undefined. Reciprocal of tangent is cotangent. Cotangent of 0 is undefined. How about if we do it for 90 degrees? Then we're drawing the angle straight up. That means that the horizontal displacement is 0, A is 0, B matches R as 1. And the ratio definitions then give for sine of pi over 2, 1 over 1 for opposite over hypotenuse, cosine pi over 2, 0 over 1 for adjacent over hypotenuse in that limiting case. Tangent pi over 2 is opposite over adjacent, 1 over 0. That's a problem. Tangent of pi over 2 is undefined. And let's do the reciprocal things. Reciprocal of sine is cosecant. Reciprocal of 1 is 1. No problem. Secant is reciprocal of cosine. 0 over 1 becomes 1 over 0. That's left undefined. Cotangent, the reciprocal of tangent. Cotangent of pi over 2 puts the 0 on top and the 1 on the bottom, and that is defined. So cotangent of pi over 2 has value 0. As we generate these values, it would be a mistake for you to just try to see this as a whole list of things to memorize. Don't do it that way. Instead, think about what the limiting case looks like by drawing a triangle in and applying the ratio definitions of the trig functions to figure out what values you should assign to these special angles. Well, we could continue. 180 degrees is pointing straight back. Sine of 180 degrees is 0 because opposite over adjacent, opposite is 0. Opposite over hypotenuse, rather, opposite is 0. Hypotenuse is 1 for that triangle. For 270, sine goes straight down, so keep track of the signed number for the y coordinate. That would be -1 when you go straight down 1 unit on the y-axis. So -1 over r is 1, makes -1 the value for sine. And we can continue to calculate values of the trig functions for other special angles coming out to be these quadrant angles, 0, 90, 180 degrees, 270 degrees, and coming up with the ratio definitions to see what values arise. Not defined happens for functions that have a ratio with a 0 in the denominator. So look at the triangle, sketch in a reference triangle, and if the triangle in the limiting case goes to a ratio definition of a trig function with a 0 in the bottom, the trig function would be just reported as not defined. We can keep track of the signs of the trig function, where they're positive and where they're negative, by looking at the coordinates of points in each quadrant. In quadrant 3, A is negative and B is negative, R is positive, and that's relevant for figuring out the ratios. Sine would be opposite over the hypotenuse, a negative number over R. R is always taken to be positive, so negative over positive is negative. Sine is negative in quadrant 3, and so is cosine. In quadrant 1, both A and B are positive. In quadrant 2, A is negative, B is positive. Go back X direction, up Y direction. In quadrant 4, A is positive, positive X direction, side adjacent, negative Y direction. So what this gives is the ratios that you can keep track of, signs quadrant by quadrant, to see what comes out for the trig function. Since both A and B are positive in quadrant 1, all the trig functions are positive in quadrant 1. In quadrant 2, side adjacent is negative, side opposite is positive, negative x, positive y. That makes sine positive and the reciprocal of sine positive. All the other trig functions are negative in quadrant 2. In quadrant 3, sine and cosine are both negative because you've got a negative x-coordinate and a negative y-coordinate to get to a point in quadrant 3. So sine and cosine are negative. Since you've got a negative divided by a negative for opposite over adjacent to calculate the tangent, that would be positive overall. Negative divided by negative is positive in quadrant 3. So tangent's positive there. Cotangent, its reciprocal, is still positive, and all the other trig functions are negative in quadrant 3. In quadrant 4, with a positive x and a negative y, we get adjacent, positive, opposite, negative. So the cosine adjacent over hypotenuse is positive, and its reciprocal is positive, and the other trig functions are negative. I have heard this little mnemonic to keep track of things as you work your way around from quadrant 1 to 2 to 3 to 4. Keep track of where the positive values are. They're all positive. S for sine is positive. T for tan is positive. C for cosine is positive. So I've heard it be like all. S for students. T for take. C for calculus. All students take calculus. That's not true, but it makes a nice pattern to see which trig functions are positive in which quadrants. So we're keeping track of general angles by doing right triangle trigonometry. For an angle that is bigger than 90 degrees, we can drop the perpendicular from that angle to the x-axis and build an acute angle based on that angle, and that acute angle is an angle in a right triangle. It's what's called the reference angle. So here's what it looks like in quadrant 2. The general angle is an angle bigger than 90 degrees, between 90 and 180 degrees. But when we drop a perpendicular from the terminal side of the angle to the x-axis, in this case it would be the supplement of that angle that is the acute angle that you build in that right triangle. That's what's called the reference angle. So we can keep track quadrant by quadrant how big the reference angles are. For quadrant 1, the reference angle is the angle itself. No problem with it being acute. For quadrant 2, drawing the angle around to a terminal side in quadrant 2, the balance of the angle, the part between the terminal side and the negative x-axis, is the reference angle, and that would be 180 minus the angle, or if it's in radian measure, pi minus the angle as the reference angle. In quadrant 3, it's bigger than 180 degrees, so drop it back to 180 degrees to get the perpendicular dropped, and that would be the reference angle. In that case, it would be theta minus 180 degrees, or in radian measure, theta minus pi. And if it's in quadrant 4, not quite up to 360 degrees, the extra bit to get to 360 degrees is the acute angle missing in quadrant 4. So that's the reference angle in quadrant 4, either in degree mode or in radian mode. So if you've got a general angle that's pretty big, that doesn't fit as an acute angle, the trick to figuring out what the value of the trig function is to drop it back and find a reference angle in the appropriate quadrant. So let's do these two examples. First, cosine 570 degrees. Well, 570 degrees is a whole way around 360 and a little bit more. The more part is 570 minus 360, so 210 degrees more. 210 degrees puts you from, let's draw in, let's put in the reference axes. So here's an x-axis and a y-axis. Work your way around 90, 180. 210 is 30 degrees past 180. So a 30-degree triangle in quadrant 3. That means that cosine is negative in quadrant 3. The 30-degree angle in quadrant 3 has a value of cosine root 3 over 2. So since it's negative, minus root 3 over 2 would be the value of cosine of 210 degrees, which is cosine of 570 degrees. Now let's do this tangent. 16 pi over 3. 16 pi over 3, well, let's march around. 1, 2, 3 pi over 3 is pi. 4, 5, 6 pi over 3 is 2 pi. That's one full revolution. We can ignore that. 6 pi over 3, 12 pi over 3, around again. And 2 pi over 3 is 2 pi is 6 pi over 3. So we've got to figure out an angle of 10 pi over 3. 10 pi over 3 is more than one full revolution. In fact, it's 4 pi over 3 past one full revolution. So we'll do a reference angle of 4 pi over 3. Again, you can do it in your head, sketch in axes. 1, 2, 3 pi over 3 is pi, that's 180 degrees. 4 pi over 3 is an angle that is pi over 3 past pi. That's in quadrant 3. So we need to go quadrant 3 where tangent is positive, and it will be the same as the tangent of the reference angle of pi over 3. That's the excess over pi. We saw pi over 3, that was 60 degrees. Tangent of 60 degrees was root 3 over 2. So root 3 over 2 is the value for tangent of the angle as it was given. Work your way around and around to come up with the reference angle in the appropriate quadrant and get the plus or minus correct based on whether the ratio of sides is the signed arithmetic positive or negative. And that's how you do general angles.